Okay, so it's already time, so I'm going to start my today's session. As you know, in the last class, we started discussing about walk, path, and circuit, and also subgraph. And this is the diagram, tree diagram, where you can have a connection between these four components. So first we start with the subgraph, and then from every subgraph we can find a walk, and walk can be divided into two different categories. One is called path and another is called circuit. The fundamental difference between path and circuit is that in path is a kind of open walk in which no vertex appears more than once. No vertex appears more than once. And here also in circuit, no vertex appears more than once. The only difference is this is a closed walk. And this is true except the terminal vertices from which the circuit begins and at which the circuit ends. So apart from the terminal vertices, the intermediate vertices will not appear in the closed walk. So these are the two fundamental difference between open walk and closed walk. And in general, in walk, no edge appears more than once, but vertex may appear more than once. Okay, so since path is a kind of walk and circuit is a kind of walk, so also in path and circuit, edge is not appearing more than once. So what is the fundamental difference between path and circuit and walk? The difference among these three is that there is a similarity between among all these components. In all these components, edge is not being repeated, but in walk, vertex can repeat itself. So vertex is a kind of the walk is a kind of alternating sequence of vertices and edges, where vertex can repeat itself, but edge cannot. But path is also a kind of alternating sequence of vertices and edges, where edge is not appearing at all because path is after all a walk. But along with this, vertex is also not repeating itself. Closed walk is also kind of alternating sequence of vertices and edges, where edge is not repeating itself, but also vertex will not repeat itself until unless they are terminal vertices. Okay, so you have to remember this particular tree diagram to remember the notion of these four categories. Okay, so let's proceed with our next topic of graph theory, which is very important and which is about connected and disconnected graphs. So let's find out the definition. So connected graph is a kind of graph where between every pair of vertices, you can get at least one path. So that kind of graph is called a connected graph. So it is quite obvious that if you can have a pair of vertices in a graph between which you cannot find any edge, then this graph will be called a disconnected graph. Say, for example, let me show this by a figure. Suppose I am considering this straight line, or suppose I'm considering this triangle. Okay, so this triangle, I am naming the vertices as V1, V2, and V3. Now you see that if you consider any pair of vertices of this particular graph G, between every pair of vertices, there is a path. There is a kind of edge exists, a path exists. Paths are actually edges, you know, because edges are actually part of paths. So between every pair of vertices, you can have at least one path. Why this word at least is there? Because it is not like that we always talk about the simple graphs. Between the pair of vertices like V1 and V2, you can have a parallel edge also. So by two edges, they may be connected to one another. Okay, and you can have the diagram like this also. So therefore, this word at least is given. So if you can find at least one path between every pair of vertices in the graph, then we say that this graph is a connected graph. But suppose there is a graph like this, and between the pairs 1 and suppose this vertex is 3, between the pairs 1 and 3 you are unable to find any path, or between the pairs 2 and 3 you are unable to find any path, then we shall call this type of graph as a disconnected graph. So if I consider this as a whole, then we can name this graph as G prime, and we'll say not only that this graph is disconnected, but also that this graph has two components. So next comes, if we talk about the disconnected graph, then there is a notion, an extra notion come into play, which is called the component of the graph. Which particular, now as you know that in the graph, there are two important sets. One set is the vertex set, the set of vertices, and another set is called the edge set, the set of edges. When we talk about components of graph, and if I say that a particular graph has two components, as is the case with the graph G prime, that means G prime actually consists of two vertex sets. So we can get two vertexes V1 and V2 in G prime. Since there are two vertex sets in G prime, therefore the graph G prime is actually a disconnected graph. In one vertex set, we have the vertices 1 and 2, and in another vertex set, we have the vertex 3. And when we combine V1 and V2 together by the operation union, we get 1, 2, and 3, which define all the vertices of the graph G prime. And we can name this vertex set as V. So combination of these two vertex sets gives you all the vertices of the graph G prime. Okay, but again, you consider this particular figure, and suppose we are connecting the two dots 1 and 2, and also I'm connecting the dot 3 and 2. Then again, this particular vertex, this particular graph is not a disconnected graph, because we can find a path between the pair 2 and 3. Maybe there is no such path between 1 and 3, but we can get a path between 2 and 3. This type of path. Now you can have a doubt in your mind that as it is written here, that in graph, there must exist at least one path between every pair of vertices. So you can ask me this question that between the vertex 1 and 3, there is no such path. As we can see that they are not joined. So how this particular definition is going along with the given diagram. If I name this graph as G prime, I will say that this particular graph is connected. Why? Because between the pair 2 and 3, we can have a direct path, but between the pair 1 and 3, we may not have a direct path, but we have an indirect path, not undirected, indirect path. What is this? What is this path? We can consider, if I name this edge as E1, and if I name this edge as E2, then between 1 and 3, we can get this kind of sequence, E1, 2, and E2, 3. So this is a path, okay? And no vertex is repeating itself over here. So Maybe there is no direct connection between the two vertices, but we can have indirect connection between the two vertices, and therefore the definition of connectedness is not being violated for the graph G double prime. So the notion of connectedness and notion of disconnectedness is a very important notion in graph theory. Okay, so let's proceed further. I am skipping a few lines from the book that you have all the book already with you. So you will go through the lines line by line, and you will definitely, you are going to understand what are they actually saying. I'm just discussing the important parts. Now, as for example, with respect to this theorem 2.1, I'm just going to read the theorem, and you are going to understand what does it actually mean, but I'm not going to discuss the proof, because the proof is explicitly written over here. So you can go through the proof at any point of time. So for example, this theorem states that a graph G is disconnected if and only if its vertex V can have partitioned into two non-empty disjoint subsets V1 and V2 such that there exists no edge in G whose one end vertex is in subset V1 and the other end in the subset V2. I can at least talk about the meaning of the statement that is given over here. Now you can see that the graph that they have drawn, if I name this graph as capital G, this graph has got two components. One component is G1 and another component is G2. Now in G1, we have got 5 different vertices. And in G2, we have got 4 different vertices. Okay, now 2 vertex sets are there actually. And if I take the union of these two graphs, we are actually getting, we're actually going to get the entire graph, which is capital G. Now, the theorem is saying that this graph will be connected graph. If I say that this graph is connected, this graph is disconnected, then we cannot find any edge, say I'm considering this edge virtually, this edge E, where the one end of the edge, that is, let us consider this one end of the edge to be V1 and another end of the edge, let us call it as B1 prime. So if the graph is disconnected, it cannot be so that V1 belonging to the vertex set of the graph G1 and V1 prime will belong to the vertex set of the graph G2. We cannot get such edge for this type of case. But if the graph is connected, then we can get such this type of edge where one end of this particular edge will be in one vertex set and another end of this particular edge is in another vertex set. But this is not going to happen over here. And if you ask me that how many components are there in this type of graphs, I'll say that there are 2 components in the graph, because there are 2 different vertex sets and therefore there are 2 components. Okay, so and also the theorem is not only a one unidirectional, this theorem is actually bidirectional. So if the graph is disconnected, so it is going to be set, this particular property is going to be satisfied, and if the graph is actually satisfying the given property, then the graph will be known as a disconnected graph. Okay, so you just go through the proof as it is mentioned over here. I'll ask you to go to read the proof, because in graph theory, whenever you are going to deal with a problem, these solved examples or solved proofs will help you to get acquainted with the process by which the problems can be dealt. And this theorem 2.2 is also very important and is also very useful sometimes, that if a graph is connected or disconnected, this whether you consider a graph which is connected or disconnected, this type of graph has exactly 2 vertices of odd degree, and if this happens, then we can say that there must be a path joining these two vertices. Okay, so let us try to understand the meaning of this particular theorem. Suppose I am considering this this particular graph, which is a very simple graph. Okay, it is a connected graph, of course. So we have three vertices over here. Now, what is written? It is written that if a graph which is connected has exactly two vertices of odd degree, so you see that in this particular graph, if I draw the graph in this particular manner, the vertex 2 has degree 1 and vertex 3 has degree 1. So both the vertices are having odd degree. So how many vertices are having odd degree here? Two vertices are having odd degree here. And therefore, you can get a kind of path which joins the two vertices. Okay, so this is also true for the disconnected graphs. Okay, so this theorem is sometimes very useful for us to solve the problems. So let's proceed further. And here comes the most important theorem again, I'm not going to talk about the proof which is written over here, but of course, I'm going to talk about a problem which is there in the exercise, and I'm going to take the help of this particular theorem to do that exercise. Okay. Theorem says that if I consider a simple graph, and you know that the simple graph is a kind of graph which has no parallel edge and no self loop. And in this simple graph, if we have n vertices and k components, then this simple graph can have at most n minus k into n minus k plus 1 by 2 edges. Okay, now this is the generalized version of the proof that we did in our previous class. What we did in our previous class, if you can recall, that we did a similar type of problem where we showed that for a simple graph, if small e is the number of edges and small n is the number of vertices, then the maximum number of edges is n into n minus 1 by 2. We proved this result in our last class. Now, which was not told to you in that particular proof is that we not only considered the simple graph, but also we considered a kind of connected graph. I didn't say anything about this because the notion of connectedness was not introduced in the last class. Now, since I have introduced the notion of connectedness and disconnectedness, and you know what do we mean by components, so let's try to figure out whether this particular result that I proved in the previous class, whether this can be made a special case of the given result, which I have underlined over here. Now, suppose we are considering a simple graph, which is connected. In that case, what is going to happen is that for a simple graph, we have, suppose we have n number of vertices and small e number of edges. But since we are considering the connected graph, then the number of component of the graph will be 1. Because only one component, that is only one vertex set is present. And if I substitute these figures in the result of the theorem, what we are going to get, if I substitute k equal to 1 over here, we are going to get n minus 1 into n minus 1 plus 1 divided by 2, which is of course n into n minus 1 by 2. And the word at most is already there, which means that your number of edge is actually either less than this value or equal to that value. Okay, so we have seen that this particular result which you proved for a simple graph, it's actually a special case of the given result. And not only this, this particular result is also true for disconnected graphs also. Say for example, let us try to figure out whether this result is valid for the disconnected graph which has been shown above. Now in the in the previous page, we had this disconnected graph. Okay, so let us try to calculate. Let us try to figure out whether this result is being violated or being satisfied by this graph. If I consider this as an entire graph, it has two components. So here k is equal to 2. And in the first graph, that is G1, the number of vertex, this particular graph has a few vertices, and in the component G2, it has a few vertices. How many vertices are there? Let us try to find out. In G1 and in G2, the number of vertices, let us denote this by N1 and this by N2. We have in G1 5 vertices, and in G2 we have 4 vertices. How many edges, how many components are there? And in total there are k components. That means 2 components in this particular graph. So if I consider that E is the number of edges, E is the number of edges of the graph capital G, which is G1 union G2, according to the theorem, E must be less than or equal to n minus k into n minus k plus 1 by 2. Now this implies that this must be less than or equal to, what is n? Here, remember, since this is a disconnected graph, n is equal to n1 plus n2. So here n is 9, k is 2, and here n is 9, k is 2, and plus 1 by 2. So this implies E must be less than or equal to 7 into 8 by 2. And this is E must be less than or equal to 28. And obviously the number of edges that have been drawn over here, this is less than or 28, of course. Okay. And you cannot make more than 28 edges in this particular case, because if you try to do this activity, then probably your graph will no longer remain disconnected. Okay, so you can figure it out yourself. So this particular result, the theorem that I have described, is actually very useful result. And now I'm going to prove one exercise, one problem taken from the exercise, where I'm going to use this result. But I'm not going to explain the proof over here, because it is well written, and you can if you go through it properly, and you will be able to figure it out yourself. Okay, but if you find any difficulties in proving this result, then you can always knock me. But right now I think that memorization of this particular result will only be sufficient for you to for your upcoming examination. So let us go to the exercise part, and let us try to solve that problem for which I'm talking about. So suppose this result I'm going to do for you. Question number 2.8. Prove that a simple graph with n vertices must be connected if it has more than n minus 1 into n minus 2 by 2 edges. The purpose of showing you the proof of this result is to show you that we always have the notion in while doing mathematics, that our mathematical problem will always be a numerical problem. If the problem is not numerical, then it is not a problem. It is something we like to call as result, theorem, or corollary, or lemma, or whatever. But in graph theory, the situation is entirely different. Nothing is theorem and nothing is problem. Everything is theorem, can be regarded, every problem can be regarded as a theorem or can be a problem. So if you consider the theorem 2.3 that I talked about just now, if you consider that to be a theorem, then your question number 2.8 becomes a problem. If you consider this problem as a theorem, then your problem theorem number 2.3 becomes a problem. So you cannot distinguish between the problem and the theorem. Here I'm going to talk about how to make use of the existing theorem to prove different results of graph theory. And that is why I'm showing you how to prove the given problem. First of all, we are going to write the statement with our usual notion of mathematical logic. We shall consider two statements P and Q. Our statement one is that our statement P will be a simple graph with n vertices, has more than n minus 1 into n minus 2 by 2 edges. This is my statement 1, or statement P. And my statement 2, Q, is capital G. Let us call this simple graph as capital G. Statement Q is that G is connected. G is connected graph. Our objective is to show, according to the problem, is to show that P implies Q. And also from mathematical logic, we know that this particular thing is equivalent to not Q implies not P, if you can recall. So I'm going to make the result, I'm going to prove this particular result in a contrapositive manner. So I'm starting. If possible, let minus Q is true. Okay, that is the graph which is simple and which we denote by capital G be not connected. Be not connected. If it is not connected, then immediately we can say that G has more than one component in it. G has more than one component in it. Suppose, without any loss of generality, that number of components in G is small k, which is 2. So we are only considering 2 components for the disconnected graph. We can consider more than 2 components also, but as I have mentioned, without any loss of generality, I'm only and for the sake of simplicity, I'm considering only 2 components over here. Since capital G is simple graph, with n vertices and k equal to 2 components as per our assumptions, by theorem 2.3, if I consider E to be the number of edges of the graph, G, this must be less than or equal to n minus k into n minus k plus 1 by 2. And if I substitute the result, I mean the value for k, we will get n minus 2 into n minus 2 plus 1 by 2. And this becomes number of edge is less than n minus 1 into n minus 2 by 2. But what is capital G? We can name this as equation number 1. What is capital G? We considered here that our capital G is not connected. Capital G with the given property. With the given property is not connected. What is the given property? Given property that it has more than n minus 1 into n minus 2 by 2 edges. But here, if I assume that the graph is connected, not connected, then we are actually getting this result, which violates the given property for the graph G. And why it is getting violated? And if it is getting violated, that means this implies minus P is true. Okay, so this particular property that we assumed over here, it is wrong, but which is not, because this is the property which is given to us. And therefore, we are actually, by using this notion, we are actually reaching to a contradiction. So we reach to a contradiction. Contradiction to the fact that the given property is not correct. Given property about G is not correct. And this contradiction is actually appearing because we wrongly assumed that graph is not connected. And therefore, this implies capital G is connected. So the problems of graph theory are actually very intricate, and if you give some time, if you dedicate some time to it, you will find it very interesting. But if you do not have the time for sitting quietly at some place and thinking over the problem which you have in front of you, okay, and if you ask for only applications, then this particular subject matter is not for you. Okay, so and why do we need graph theory? Is because suppose we are actually designing a circuit. So in circuit designing, graph theory is actually very helpful. In circuit designing, we want to embed some sort of algorithm with respect to the circuit on the chip. Now, a particular point is there from which we have to build a path from that particular point to another point, which is at the end of the chip. From top to bottom, we have to build a path. Graph theory actually plays a very important and fundamental role in this particular respect. Okay, but graph theory is actually very complicated, and you have to dedicate lots of amount of time to study it. You will be encountering graph theory in its various phases in different parts of your computer science syllabus. Okay. Say, for example, and one particular drawback with graph theory is that it has lots of different definitions, and it is also very important, and it is also fundamental requirement which is important, that we need to remember those definitions. Say, for example, this Euler graph, this definition, Euler graph is actually very fundamental, and you have to remember what we mean by Euler graph. Euler graph is a kind of graph which has Euler line. What is Euler line? In a type of graph, if we can find a closed arc running through every possible edge of capital G exactly once, such a line is called Euler line. And if a particular graph has this kind of property also, the graph is called Euler graph. Things looks very complicated to you, I think. You have not understood what is written in the paragraph, but if you read carefully, you will be able to understand it. I have activated the chat box. You can put your attendance over there. Now, what is it saying? When we started defining work, what did we mention? We mentioned that in work, edge cannot repeat itself. Edge cannot repeat itself. Okay, and in defining path and circuit, we are only busy in making the points that the path and the circuit shouldn't contain any repeated vertex. If you can find a particular graph where the circuit is present, that means the vertex is not being repeated, but you can find an edge also, the edges also, which is also not repeat itself. So circuit is not in that particular circuit, the vertex is not being repeated, the edge is not being repeated. In this type of graph is actually called the Euler graph. Okay, the best example to understand Euler graph is this one, this triangle, the geometric figure which we learn in our childhood. You see that this is a circuit. You can start from the vertex V1 and you can move along these edges and you can come back to it. In this particular case, no vertex. If this is the starting point, if this is the starting point, then V2 and V3 are the intermediary points. Now, these intermediary points are not being repeated. You are covering V2 only once and V3 only once. Okay. And V1 is being repeated because V1 is the terminal vertex. So the vertex related property is being satisfied over here. Not only this, if I move along this direction, all the edges are being repeated only once. All the edges are being repeated only once. So this particular graph which we have over here is called the Euler graph. And one is a very important and fundamental property for the Euler graph is that if you can find an Euler graph, then every vertex will be of even degree. If I consider the vertex V1, it has degree 2, similar to the degree of the vertices V2 and V3. So Euler graphs, if you can find an Euler graph, how to identify an Euler graph? You can identify an Euler graph mathematically by counting the degrees of the vertices. Why am I mentioning this particular thing to you? It is because of the following fact. Actually, it is a theorem which goes like this. A given connected graph, capital G is an Euler graph if and only if all the vertices of capital G are of even degree. The proof is actually a little bit complicated. You can go through the proof. You can read the lines carefully to understand what is written over here. But the application of this particular result is actually very important. And I'm going to talk about the application of this result in the next session of today's class. Let me stop over here and let's meet again in the next session.